Today we are going to start chapter number 6 of your course, which is about capacitance and inductance. And this chapter we are going to introduce two passive energy storage devices, that are capacitors and inductors. So the main content of this chapter is to introduce you with the concept of capacitors and how they are modeled as a circuit element. And then we'll talk about inductors and how they are modeled as the circuit elements. And at the end, we will see how capacitors and inductors are combined in series or parallel combination. As we have seen for resistors, we have seen how resistors are added in series and parallel. We will see the similar details about capacitors and inductors. So today we are going to talk about capacitors and how they are modeled as circuit elements. So let's start today's lecture. Let's talk about capacitors. So these are the first energy storage devices to be discussed. So these capacitors come in different shapes and sizes. Here we can see some examples of typical capacitors. They come in different sizes. Here we can see a capacitor can be as big as this, and it can be as small as this. And in this figure, we can see this big capacitor, which is much larger than this capacitor. But the capacitance of this capacitor is only 68,000 microfarad, whereas this one is much higher than this, which is 100 farad. So this shows that it does not depend what is the actual size of the capacitor. It is the capacitance of the capacitor that really matters. So let's talk about what capacitor is and how we define the capacitance of a capacitor. So in order to define the capacitance of a capacitor, we consider the basic parallel plate capacitor case. So in this case, we have two parallel plates, and in between these two parallel plates, we have a filler material with the specific dielectric constant. And let's say the dielectric constant is epsilon. So this is the material that is between the two parallel plates, and its dielectric constant is epsilon. And the area of the plate is A, and the distance between the two plates is D. So the capacitance of a capacitor can be defined as is epsilon times area over the distance between the two. So this expression actually tells us that the capacitance of a capacitor is directly proportional to the dielectric constant of the filler material. It is directly proportional to the area of the plate, and it is inversely proportional to the distance between the two plates. So all three factors, they actually account for the total value of the capacitance. Okay, so let me just clear it. So the circuit representation in case of capacitors would be as such that a capacitor will be connected like this in a circuit. So this is, for example, this is a circuit, and you have terminal positive and negative, and the voltage across these terminals is V of t. And if you connect a capacitor in this circuit, which is represented by this symbol, as we have seen that resistors are represented as this symbol, we can represent capacitors as two parallel lines, and the voltage across this capacitor would be same as this V of t, and the current that is flowing through this capacitor would be equal to dq by dt, where q is the charge flowing per unit time. We have already seen current is charge per unit time, and as we know that capacitors, they store energy. We already know how do capacitors store energy. Capacitors, they store energy in the form of in their electric field. As we can see in this example, that if we have positive terminal here, negative terminal connected here, this plate will have positive charges, and the bottom plate will have negative charges. And we know that these charges, positive charges, they have electric field going out of these charges, and the negative charges, the electric field is going inward to these charges. So because you have concentration of positive charges on the top plate and concentration of negative charges on the bottom plate, an electric field will be produced going from the positive plate to the negative plate. So the energy stored by the capacitor is stored in this electric field. So the charges that are stored here, let's say it is Q of t, and the current that is flowing through this capacitor is dq by dt. So this is how we actually represent a circuit in which we have connected a capacitor. So let's talk about the two different types of capacitors. And again, it is important to use the passive sign convention as we have seen it for the resistor cases. So now let's talk about the representation of capacitors. So there are two types of representations. One is this one, where you have one plate which is a flat plate, and the other one is the curved plate. So this kind of representation is used for the polarized capacitors. What are polarized capacitors? Here you can see this kind of a capacitor which has one leg longer than the other. This is a polarized capacitor, and the longer leg will always be connected with the positive terminal. But in some cases, you can see here, you can see both the legs are same, both the legs are same. These are the unpolarized capacitors. So unpolarized capacitors, it really doesn't matter which side you connect with positive. So for the unpolarized case, you use two parallel lines as a representation. So you can connect either of these terminals with positive or negative. But for polarized capacitors, you must ensure that the flat side or the longer leg of the capacitor is connected with the positive terminal. So this is an important point. So the curved version indicates a polarized capacitor which must always have the positive polarity of voltage on the flat side. And this is how we connect that capacitor. Here we can see it is a representation of a polarized capacitor, and the flat side is connected with the positive terminal. So in order to determine the relationship of current and voltage, the current through capacitor and voltage through voltage across capacitor, we need to look at some derivations, and we will see how we determine the relationship between the voltage and current in case of capacitors. So in order to determine that, let's talk about how we determine the voltage and current relationship in case of resistors. So if you remember, for the case of resistors, we developed the Ohm's law, which is V is equal to IR, that actually defines how voltage and current are related to each other in case of resistance. For capacitors, the capacitors, they obey capacitance law, and the capacitance law states that the amount of charge stored in a capacitor is a function of the voltage that is applied across the capacitor. So by using the same approach, we say that the capacitors, they obey Coulomb's law, and with this we can write the charge stored by the capacitor is equal to the capacitance time the voltage across that capacitor. So it is a similar expression as we have seen for Ohm's law, but in case of capacitors, we see capacitance law, which says the Q is equal to CV, which is the charge stored by capacitor is directly proportional to the voltage across that capacitor. And the constant term we see over here is the capacitance, which we have seen earlier, which is which depends upon these variables. So in this case, this C is called the capacitance of the device and has a unit of charge per voltage. So from here, if you find out C, C is equal to Q upon V, and Q is the charge and V is the voltage. And if we talk about the units, so the unit of capacitance is farad and its unit is coulombs per volt. So we know for charges the unit is coulombs, and for voltage it is volts. So 1 farad is defined as the capacitance of a device that can store 1 coulomb of charge at 1 volt. So if any device that can store 1 coulomb of charge, if a 1 volt is applied at its input, we can say it has a capacitance of 1 farad. This is how we define the units of capacitors. So let's look at an example. We need to determine the voltage across a 2 microfarad capacitor which is holding 10 millicoulomb of charge. So in this case, we are assuming that there is a capacitor which has a capacitance this, and it is holding this much amount of charge. So what is the voltage that will be appear at the terminals of the capacitor? So we can make use of this rule, Q is equal to CV, and from this we can find the value of V. V will be equal to Q upon C. So if you substitute the value here, C is 2 microfarad and the charge is 10 milli. So the amount of voltage that will appear at the terminals of the capacitor is 5000. So here we can see if the charge is in coulomb and the capacitance is in farad, the voltage will come out to be in volts. So in this case, we can see if a capacitor which has a capacitance of just 2 microfarad and it is holding just 10 millicoulomb of charge, it will have a huge voltage at its terminals. That's why we say that capacitors can be dangerous as well. So it's always better. It's always important that whenever you are dealing with capacitors, make sure they are completely discharged before you use them in any experiment. Otherwise, um, they are already charged, they would have a huge amount of voltage available at its terminal, and that can give you a shock while handling those capacitors. So another important point here is that capacitors can store and release electrostatic energy. They cannot create energy. It's just an energy storage device. It cannot create energy itself. So the capacitor is a passive element, and it also follows the passive sign convention. So as we have seen this circuit before, so if you apply a voltage V across a capacitor, it will hold a certain charge Q of t, because the amount of current that would be flowing through it will be equal to dq by dt. So in this case, we can have a linear capacitor representation. So this whole circuit can be represented in this way, where we can see we have a capacitor C, the voltage across it is V of t, and the current that is flowing through it is I of t. So we need to write down an expression that can relate the current and voltages together. So as we have seen that Q is equal to CV using the capacitance law. So Q is equal to CV. If we derivate both sides, so it would be dq by dt, and C is a constant, so C will come out of the derivative, so it will be equal to dV by dt. And we know that dq by dt is nothing else but I of t, as we have seen over here. So in this case, the current and voltage can be related with each other using this expression, which is one of the important expressions that we will come across in this chapter, that current through any capacitor is equal to C times derivative of the current, or changing voltage across the capacitor. So I is equal to C dV by dt. This is the differential form of the capacitance law. So let's talk about this. So let's look a little example, because we have said that passive sign convention hold in this case. So let's see this. So if we want to write the IV relationship for the following capacitors, here we can see this is the positive terminal, this is the negative terminal, this is a capacitor, this is positive, this negative, but current is flowing in this direction. So what should be the value of I of t in this case? Since current is flowing from negative to positive, we will deal it as a negative current, as we have done it for the case of resistors. So both the cases will follow the passive sign convention. So in this case, I of t will be equal to negative times C dV by dt. Same in this case, here we can see we have a negative terminal here and a positive terminal here. So this is negative, this is positive. Current is actually flowing from negative to positive. So again, current in this case will be negative as well. So make sure that the passive sign convention also hold whenever you are dealing with capacitors, just like you do it for resistors. So let's talk about capacitance law. As we have seen, Q is equal to CV. The charge stored by any capacitor is directly proportional to the voltage that is applied across that capacitor. So Q is equal to CV is the relationship. So we're going to look at two different variants of this capacitance law. We will see the integral form of capacitance law and the differential form of capacitance law, and what are the values or what are the implications of those two relationships. Let's talk about that. So if the voltage, in this case, if the voltage varies, the charge will vary, and there will be a displacement current. So as we have said, if there will be a changing voltage, the charge will also change, and because charge is changing, and we know that changing charges, the flow of charges will create displacement current. So in this case, we can express the voltage across in terms of current. How we do that? We can write down the voltage expression from this capacitance law as V of t is equal to 1 upon C times Q. So basically, we have taken V from here, and C has gone into the denominator on this side. So this is the expression that we have got now. And from this expression, we can write down this expression like this. And how we have got this? Since we know that current can be defined as I of t is nothing else but dq by dt. So if we integrate both sides, we can get Q is equal to integration I of t dt. So you replace Q by this whole expression. So this Q is replaced by this integral, which is the integration of the current. So here we have considered the dummy variable x. So the current is integrated from minus infinity to t ix dx, and then you divide it by c. You will get the expression of voltage in the form of current. So this form of capacitance law is the integral form of the capacitance law, because here we can see the integral representation. So this is the integral form of capacitance law. Okay. So we can also express the current in the form of voltages as well. So from this capacitance law, we can see uh, Q is equal to CV, and if we take derivative on both sides, dq by dt, and again dq by dt. So dq by dt will be equal to I, and on this side C is constant, so it will be dvc by dt. So we have already seen this expression, which is C dv by dt. So this form is the differential form of the capacitance law. So this is another important relationship. This is the integral form of capacitance law, and this is the differential form of capacitance law. It depends. If you want to find the current through any capacitor, we make use of the differential form of capacitance law. If you are interested in finding out the voltage across the capacitor, you make use of the integral form of the capacitance law. So these two relationships are very important to find out the voltage and current across any capacitor. So there are certain implications of these mathematical expressions. So the integral form of capacitance law, the mathematical implication is, if you look closely, this expression of voltage across the capacitor at any time t, it is the accumulation of current from minus infinity to the time t where you are measuring the voltage. So since this is accumulation of voltage, you don't expect an abrupt change in the voltage. So because of that, the value of voltage just before time t, so t minus means just before this time and just after this time will be exactly the same. There will be no abrupt change in the voltage. So we can always conclude from this assumption that voltage across a capacitor must be continuous. It will never happen that the voltage will abruptly change from one value to another. At any time you will see the capacitor, the voltage across capacitor will be continuously changing. And the second implication of the capacitance law is from the differential form of capacitance law. And in this case, we can see that if the voltage source that is connected with the capacitor, if this voltage is constant, the rate of change of that constant is zero, because we know that derivative of a constant is zero. So if this value is zero, current is zero. So IC will be equal to zero. So it means whenever there is a DC source connected with a capacitor, no current will be flowing through that capacitor. And we already know that the cases where when the current is not flowing through any element, the element behaves as a dummy element, or you can ignore that element as it is. So in this case, we can say the steady state behavior or a DC behavior of a capacitor is that whenever a capacitor is having a steady state, is in steady state, it acts as a open circuit because no current is flowing through it. That's why we also say that capacitors, they are used as DC blockers. If you want to block DC in any circuit, just insert a capacitor over there, because in case of DC, the capacitor will behave as a open circuit. So these are the two implications of the capacitance law, and we have derived those implications from the integral form of capacitance law and the differential form of the capacitance law. So let's talk about capacitors as circuit elements. So this is what we have talked about so far, that if you have a capacitor C with a capacitance C, the voltage across that capacitor is a VC, and the current flowing through it is I of C. Use the differential form of capacitance law is IC is equal to dV by dt, and the integral form of the capacitance law is this one, which is 1 by C integration of the current. That is the accumulation of current from minus infinity to t. So in this case, it is a similar expression that we have seen for voltage for resistors as well. So the current through resistor using Ohm's law is V over R, and the voltage across resistance is V is equal to IR. So here we can see how current through resistor and voltage across resistor are related to each other. Here we see how current through capacitor and voltage across capacitor, they are related to each other. So it is same as how we see the relationship of voltage and current in case of resistors. So here we are going to do a little bit more mathematical manipulations to derive another form of this integral form of capacitance law, which is more relevant to our analysis. So here we can see this integral that we have seen so far. It is the accumulation of values from minus infinity to t. So it means, for example, if this is your time scale and this is minus infinity, and for example you're accumulating current just like you're doing here. So let's say this is the value of current that you have from minus infinity to say positive infinity. So if you want to find the value at time t, this is this point. So what are you doing? You're actually finding the area of the area under the curve from minus infinity to t. So this accumulation is the integration from minus infinity to t. We can write this integral as sum of these two integrals, where let's say, let me use a different color. Let's say I consider this as minus infinity, this is plus infinity, and this terminal here is 0, which is time is equal to t naught. So what I can do is I can convert this whole integral into two parts. One could be from minus infinity to 0, and then from 0 to t. So if you add these two integrals together, it will give you the same result. So in this case, the first part is from minus infinity to t naught, and is t naught to t. And if we replace this integral with these two, we will get this expression like this. So in this case, let me just clear it. So here we can see it is the same expression, but it is from minus infinity to t naught, and this expression is from t naught to t. Why we have actually done this? Because here we can see this expression actually represents the accumulation of current from minus infinity to t is equal to 0. It actually means what is the initial voltage across the capacitor when you start using it. So the time you are going to pick up a capacitor that and plug it into your circuit, that is the time t is equal to 0. The circuit will start behaving after this instance. So this T naught will be equal to 0. If that circuit already hold a certain charge, that will be the initial charge that is available across that capacitor. If the capacitor is fully charged when you're using it, this value will be equal to 0. Otherwise, you have to take into account the initial charge that is stored in that capacitor in the form of this accumulation of current. And then once you have plugged that capacitor into a circuit, then and you connect it with the source, from t is equal to 0 to any time t, this will be the additional, you can say, amount of charge that it will hold, and it will be added to this initial voltage. So this expression is more useful in our case when we are analyzing our circuits. We will see what is the initial voltage across the capacitor at time t naught, and you can find it using this integral. And we will find this integral where the time the time the capacitor is connected to the circuit, we will accumulate this integral and find out the total voltage at that time t. When we are going to solve certain problems using this expression, you will understand in which cases we have to consider the initial voltage, and in which cases we have to just find out this part of the circuit. We will see these examples. So now let's talk about an example. So before that, the fact that voltage is defined through integral, it has an important implication. What does this implication says? It is this one. So let's look at an example. So in this case, we need to determine the current, and here we are given the voltage across a capacitor, and the capacitor is 5 microfarad. So since we need to find the value of the current from voltage, we need to make use of this differential form of capacitance law. So we can apply this relationship here. How we can find the current? Current can be found by taking the derivative of the voltage and multiplied by the capacitance. So if we look at this curve, this is the slope of the voltage. From 0 to 6, we can see the slope is constant, and we know that derivative is nothing else but finding out the slope of the line. And from 6 to 8, this is the slope of the line that we need to find. How do we find the slope of a line? We know that the relationship is y2 minus y1 over x2 minus x1. In this case, this point is, say, x1 y1, and this point is x2 y2. And here we can see y2 is 12 and x2 is 6 milli, and here, and this point is x1 is 0 and y1 is also 0. So here we're going to substitute the values in this expression. Y2 is 12 minus 0 over x2 is 6 millisecond, and x1 is 0 millisecond. So it would be, numerator will be 24. By the way, this is 24, this value. So it is 24 divided by 6 milli. 6 milli stands for minus 3. So the ratio of this function will be the slope of this line, which is the derivative of the voltage, and then you multiply it with the value of capacitance, which is C, which is 5 microfarad. So you will get the value of current for this duration. And likewise, we will find the slope of this line using y2 minus y1 over x2 minus x1, and we multiply it by the same capacitance to find out the current in that region. So in this case, let me just clear it. So in this case, we will use this relationship, and again, I is equal to C times dV by dt, and dV by dt is y2 minus y1 over x2 minus x1. The answer comes out to be 20 milliampere. And likewise, for the next case, the current comes out to be minus 60 milliampere, because the slope is negative in this case. So you can find out the value yourself. And I of t will be 0 elsewhere, because voltage is 0 elsewhere. So this is the required answer. The current in milliampere will be like this. So from 0 to 6, the value will be 20, as we have got here. From 6 to 8, the value is minus 60 that we have got here, and it is 0 elsewhere, as we have got over here. So in such cases, you might need to find the current across through any capacitor given the voltage, or it could be voltage is required and given the current is given in the problem. So this is the sort of problems that you would come across. So let's conclude the session here. In the next class, we are going to talk about the relationship of power and energy stored with respect to voltage and current, as we have seen it for the resistor cases, where P is equal to VI gave us the two relationships for resistors, that is V over R and I square R for the resistance, to find out the total power absorbed by the resistor. So in this case, we are going to see what would be the relationships of power absorbed by the capacitor and the total amount of energy stored in that capacitor. So let's conclude the session here, and we will continue our discussion in the next class. Thank you very much.